You should have your Lecture 9 notes out, measures of spread. First, we have just a little bit of notation. If we have a population of data, you remember a population is the entire set of data dealing with some particular question or issue that we're trying to understand. How do we represent a population of data generically? Well, it's a set of numbers, it's a set of points. So to represent it generically, we'll write a little set notation here. And I want to indicate that I'm talking about data. So we often use the letter X to represent a generic number. So what I'm going to do is I'm going to say I have one data point, and I'm going to call it X sub 1. I have another data point, and I'm going to call it X sub 2. I have another data point. I'm going to call it X sub 3. All right, and I'm assuming here that the population of data is some finite set, maybe a very, very large number, million data points or 10 million data points or something like that. So what do I put at the end here? Well, I have to end it with something, and I'll end it with X sub capital N. That's kind of a standard thing to do. And the idea is that, hey, I'm using a capital N. That means it's some big number, right? A million or a billion or something like that, maybe. All right, let's see. So the number of data points in this population is that number N. What about a sample of data? What we're going to be doing a lot of in this class is trying to understand things about a population of data by taking a sample of data. And we take a sample of data, analyze that, and maybe from what we learned there, we will be able to infer things about the whole population of data. So we have what we call inferential statistics, and we're heading in that direction. We're still really doing descriptive statistics, though, but that's the direction we're heading here. But for a sample of data, I want to do the same sort of a thing. I want to say I have some finite set of data points, and I'll just also call them X, and I'll say I have X sub 1, X sub 2, X sub 3, and these aren't the same X's as up here because I'm talking about a population of some data here, and here's a sample of maybe some other data set. They're not related. I'm just using the same letters. But where I'm going to differ is out here at the very end, I want an indication of my last data point, the final one, and I'll use a little lowercase n, X sub little n, and all that does is that just kind of suggests that it's a smaller number than is in the population, right? If I have the population is, all 7 billion people on Earth, maybe my sample is 1,000. So capital N would be 7 billion and little n would be 1,000, right? So number of data points, here is n. Okay, I want to have that notation out of the way, and so that sort of gives you a way to think about things a little bit. So, how do we compute the population mean? Recall that the population mean is a population parameter. We use the Greek letter mu to represent it, and we would write that as the sum of all these data points up here, so x1 plus x2 plus ... all the way out to the very last one, and then we divide by the number there are, right? You always add up all the data points and divide by the number there are. And we could write that, I'll go ahead and give you the compact notation. Sigma means sum, and what I typically would write is I would write x sub I, where I x sub I corresponds to a generic data point in this set that I'm adding up, and I write like this: I equal 1 down here, and I put the capital N up there, and that is a compact, I'm going to divide by my N, of course, but this is a compact way of writing x1 plus x2 plus x3 all the way up to x sub n. It means sum, add all the x's as you run the index from 1 up to capital N. We probably won't use that a lot. We'll use that a little bit. We will, but not that much. I just want to stress this is how we compute mu. What if it's a sample mean? The idea is the same. I add up all the data points and I divide by the number there are. But the symbol we use is x bar, and of course it's going to look just like this, but I'm using little n instead of big N, so this is nothing too surprising. Divide by little n. And we would write that as summation I going from 1 to little n, x sub I, all over little n. Okay, let's see. So that's just kind of a way to kind of encapsulate all these little ideas here about notation and also refresh your memories about computing means. All right, let's see. Let's consider two data sets. We'll come back to this soon enough. But let's consider these two data sets. I think you have them there in your notes, don't you? Yeah, you have the 3-point data set 49, 50, 51, and 0, 50, and 100. Crowding things a little bit there, aren't I? All right, pretty easy to see that whether we think of these as populations or samples is not really relevant. They have the same mean. The mean is 50 in each case, and it's easy to compute. But you notice there's a big difference here. I have the data here are spread a lot farther apart than here. So just being told that the mean is 50 is a pretty good indication. That doesn't really tell you what's going on with the data set, right? The mean is 50 here, and they're clustered together around 50. The mean is 50 here, and they're spread farther apart. So I don't get the full picture, certainly, by just getting the mean, for example. So getting this measure of center isn't really enough to tell me, give me a good picture of the whole data set. So if you recall, we had, what did I say here? We had a one-number summary, which was we often said we use a measure of center for that, such as the mean or maybe the median, right? Well, what we're going to do now is look at a two-number summary. Let me write it out, two-number summary of a data set. The first number we'll have is the measure of center. So it's giving you kind of a typical value, kind of a middle value. But what I want is I want the second number. Okay, I'm giving you a typical value, but I'd also kind of like an idea just how spread apart the data are if possible. So I'd like a measure of the spread of the data, if at all possible. All right, I would like some idea of just how spread out the data are. And then I think I have a definition here. So definition. And we're talking about here the range of the data set. And all that is the biggest data value minus the smallest. All right, let me get my page flipped here. Should have done that earlier. Okay, so if you go to the next page, we have an example. I'm certainly not going to draw that out there. What I've done is I've given you a number line, and there are a lot of data values along that number line, and then the number of dots above each data value represents the number of data points that have that value, right? And so the way it's laid out, it almost makes you think of a histogram, right? It certainly isn't a histogram, but you know, the taller stacks of dots mean you have a greater frequency of that value. Excuse me. So it gives you kind of a compact picture of the data set. What's the range? So in our example, the range is easily seen. I got the 19 way out there to the right minus the 6. So the range is 13. Okay. That is maybe just a little bit unsatisfying, as I say there. And the reason it's a little unsatisfying is it certainly does tell me how far apart the data are, but it doesn't give me a good picture of the whole data set, right? Because there's those two extreme values, 19 and 6, that give me that range of 13. Much of the data, most of it really, most of the data is clustered closer to the middle, right? And the middle is, I've forgotten, I didn't even calculate the mean. I forgot if the median is 12 or 12 and a half or something like that. Let me just say it's closer to the middle. All right, so seeing that the range is 13 might lead you to think that it's just spread all along that interval between 6 and 19, but it isn't. A lot of it's clustered in closer, just a couple of points, one out here and one out here, right, that give me that range. So I don't get a really maybe good picture of overall how spread out the data are. A better, I guess I'm going to put it in here, and I think I'm going to change my color just in case I have to run into things a little bit. I want to make sure it's all readable. A better definition is a spread of a measure of spread is the standard deviation of the data set. And I have down here enough space for you, and I say for you to write a couple of things here, and I say that the definition depends on whether you're talking about a population or a sample. So let me put in the definition of the standard deviation for a population right here. The symbol for it is the Greek letter sigma. So we write that like that. And now what we do is we take, I'm over here looking at my data set, boom, 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 and I'm looking at my population mean, mu. What I'm going to do is I'm going to take that first point and I'm going to subtract mu away. All right, so this gives me how far apart x1 and mu are. I'm going to come back to this. I got a little bit more to do here. And I'm going to do the same thing for x2. Subtract away from u plus dot, dot, dot. I'm going to go all the way out to the very last data point. All right, but what I'm actually wanting is I want some indication of how far apart these data points are. I don't want a negative difference to cancel out a positive difference. I want these all to add up. So I'm going to square each one of these, et cetera, et cetera, et cetera. I'll square each one. So what I've done is I've taken the distance between x1 and mu and squared it, the distance between x2 and mu and squared it, et cetera, and taken the distance between the last data point and the mean and squared it. I'm adding them all up. I'm going to get the average of that. I'm going to divide by the number of data points in the population. And all these squares, now what I need to do is to get a true measure of the spread. Actually, in terms of the units that I might have for measuring the data, I actually need to take the square root of the whole thing. All right, so the population standard deviation is given by that formula. What is it for a sample? For a sample, we use the letter S, and you might think it's going to be much the same, and it is much the same, but it's not quite. Of course, now I'm looking at down here at my sample set of data, and I'm going to use my sample mean because I don't have a population mean, but I have a sample mean. So I will take the first data point minus the sample mean, and this time I'll go ahead and square it, plus the second data point minus the sample mean, square it, plus keep doing that till I get to the very end. The last data point minus the sample mean squared. All right, now for technical reasons that we might discuss a little bit more later, you'd think I would divide by n under the square root sign. I'm actually going to divide by n minus 1. And there are technical reasons for that, and like I said, we'll talk about them later. Let me real quick do an example here. In fact, I'd like you to try it. So we have this really small data set, negative 7003. Okay, so it says, well, I guess it doesn't say there, but what I want you to do is think of it as a population, find mu and sigma. And then number 2, think of it as a sample, find x bar and s. Okay, please give that a try. Pause me and see if you can do it. And we'll see how you did. Okay, number 1. I think I can get all this in. Mu, we do mu first. Mu is, what is it right here? I add them all up and I divide by the number there are. So I get -7 plus 0 plus 0 plus 3, divide by, there are 4 data points, and you work that out and you get -1. Let's find sigma. Sigma is, here's my formula, so it's the square root, watch very closely, I take the first data point, -7, and I subtract the population mean. So I have -7 minus -1. I square that. Plus 0 minus -1, taking the second data point and subtracting the mean from it and squaring, plus take the third data point and subtract the mean from it and square it, plus take the last one and subtract the mean from it and square it, and all of that is over the number of data points there are, which is 4. And this is all under the square root. All right. Now I am going to just cut to the chase here. You end up getting the square root of 54 over 4. You can check that. This will be -7 minus -1 will give me -6 squared. There's 36. Plus this will be 1, this will be 1. I think this turns out to be 4 squared, which is 16. If you add all that up, you get 54 divided by 4, square root, you get about, let's see, 3.674, et cetera, et cetera, et cetera. Okay, number 2. I want to find x bar and s. Well, x bar, how do you find that? The answer is you add them all up and divide by the number there are. So the calculation is the same as it is for mu. So it's -7 plus 0 plus 0 plus 3 over 4, and you get -1. I'm about out of room here. Look, the thing I get for s is exactly the same up here, except I divide by n minus 1, which is 4 minus 1, or 3. So I'm just going to have to kind of crowd things a little. So I got the first one plus, I think I can get them all in here. Just for the sake of completeness. Yeah, 3 minus -1. So the numerator inside the square root looks like just like the same up here, but I will divide by 4 minus 1, which is 3. And when you do all that, you get, I got like 4.2426, etc. Okay, so I hope you can get those two values. We'll take a look at the importance of the standard deviation, why it's a good measure of spread in the next lecture. If we can stop this one.